Let me share my slides. Okay, can you see the slides? Please confirm. All right, thank you. Okay, we are still in the middle of wafer preparation. Okay, so we've discussed in terms of the steps that are needed in order to prepare the wafers before the wafers are characterized and are ready for the fabrication processes. Okay, so we've gone through briefly all the steps shown on this page. Let me approve some of the students. Okay, so we've discussed about the crystal growth in our last lecture, and then the removal of seed and tail from the ingot, right? Grinding of the bowl or grinding of the ingot into a cylinder, and then determine the orientation, which is essentially marking the orientation rather than determining, because we've already determined the crystal orientation during the growth process. Okay, so marking the orientation according to the flats and notch, and then we grind the flats in order to mark whether it is P type or N type, 100 or 1, and so on and so forth. Cutting the ingot into wafers, and then we're going to cover next process as well. Edge rounding, and then lapping the wafers to the correct thickness, removing the damage, and then mechanical polishing, mechanical polishing, and then wrapped up by chemical cleanup before we perform characterizations on the wafers. So, right, so this is actually the same thing. Okay, the same flowchart more or less. So involving from crystal growth to shaping, crystal, slicing, grinding, etching, polishing, and then inspection. So let's move on to the slicing of the wafers. So we can do using multiple techniques of the slicing process. So if you can see from this first slide for this topic, we can use diamond blade, for example, in order to cut the wafers into a specific thickness. Okay, so the thickness is determined by the foundry, if you like, and the wafer fab. So typically for wafer fab operation, we use thickness somewhere around 500 micron. Okay, in order to do the fabrication process. Where if you talk about solar industry in particular, we are now using about 180 micron. Some companies are using 160 micron. So that's like 2 or 3 times thinner than what we use in IC industry. Okay. So let's see the process in particular. So this can be done by diamond saw, or we can also use diamond wire saw, right? So the diamond saw is as shown in the first pages now. So we use the physical sewing, right? The diamond blade, macam blade yang keras, right? So on the other hand, you can also use wire saw, but then it's made of diamond. Okay, so it's equally strong to cut the wafers into pieces. So for example, if you look at wafer sawing using wire sawing, okay, wire saw, for example. So this is particular for solar industry as an example. So you can, if for you to cut, say 140 to 160 micron space, so wire covered this this is actually the diameter of the wire, 140 to 160 micron of the wire covered with an abrasive liquid. Abrasive ni macam rough particles, particles that you can use around the wires in order to enhance the cutting process, in order to increase the efficiency of the cutting process. So dia punya effect dia more or less like kalau you pakai sandpaper kan, you pakai sandpaper kan, you can feel the roughness of the surface, isn't it? So that roughness is transferred to wire saw punya process, diamond wire saw. So you can use that abrasive liquid. So essentially liquid with abrasive. Okay, so you can use PEG or silicon carbide slurry in order to be the abrasive. So in the solar industry, we call this as multi-wire slurry source. Process is quite slow. Wires have to be changed regularly, depending on number of wafers that we cut. Okay, so typically it's done every day. So generate a lot of waste. Okay, so we have large curve losses, about 200 micron. So the curve loss is something like, have you seen people cutting logs? Pernah tengok tak orang potong kayu pokok ke ataupun kayu untuk buat furniture, for example? Have you seen any of those, the cutting process? Kalau pakai gergaji elektrik kan? Okay, pernah tengok eh? So when you, for example, if you see people cutting kayu balak ke, for example, kat TV ke YouTube ke. So when you cut between, hold on, let me improve students, hold on. Okay, bila you tengok orang potong kayu kan, so bila, for example, you have kata you ada kayu balak, for example, then you want to cut using the machine, you want to cut to small pieces. For example, you nak buat table furniture dekat table untuk kawasan rekreasi, for example, you buat bulat kan. Okay, so bila you cut between pieces, what do you see? You cut between the first piece and the second piece. Apa yang you dapat kat tengah while doing the cutting? What do you see? Let's imagine the log first. Kayu dulu kayu balak, kayu whatever. What do you get in between while doing the cutting? Anyone? Sebelum kita discuss on the wafers, we discuss kayu dulu. What do we see? Kalau kita potong kayu, exactly, right? So you nampak habuk dia terbang-terbang kan? You nampak habuk kan bila potong tu kan, usually the person who operates the machine akan pakai mask or whatsoever ataupun shield completely sebab ada habuk kan. So that habuk, habuk bila you potong pokok tu is essentially the curve loss while cutting the wafers. So dia akan ada habuk jugalah sama. Cumanya habuk dia instead of kayu, then habuk silicon lah. So that's what we call curve loss, right? So this is it, curve loss. So if you cut between wafers, so if you imagine this, for example, this, so ni ada banyak wire between it, so you might have like 50 or 100, for example, and you may have like this wires in series. So between every cut, so this wire, bila you cut the ingot, katalah you ada, in this case is not is more of brick it's more of brick, tapi you can also imagine cutting an ingot, cylindrical ingot, for example. In this case, it's represented by bricks. Sebab kita, kalau solar cell, kita nak pakai in rectangular form rather than in circular form. Okay, sebab kita nak maximize the area of energy harvesting on the panel later on. So that's why we need to have all areas covered on the solar panel. Tapi kalau imagine this to be cylindrical silicon, so it works the same way, exactly. So bila you potong, so the area yang you ada, the areas where you have the wires, you're gonna suffer from curve losses ataupun curve loss. Okay. So maksudnya if I can draw this, like that. Katalah let's imagine this cylindrical cylinder. cylindrical silicon, sorry, from the cross section. Kita tengok dari tepi ya, and it's like that. It's long. Then you have your wires, say here, cutting here. Then you have your wire cutting here. You have your wire cutting here. So that means the area that you are cutting here, there you akan ada habuk tu kan. So you akan potong. So this will be your wafer thickness, for example, and maybe another one. Maybe this will be your wafer thickness. But in between, you're going to have these curve flaws. Okay, so curve flaws damage on either side. For example, if you use this diamond wire saw, you're gonna lose about say 10 to 20 micron on either side of the wafer. So that means bila you potong wafer yang kat tengah, so you might be losing say 20 micron on the left hand side of this wafer. Sorry. Kenapa black screen pula? Yeah, on the left hand side, say you lose about 20 micron. On the right hand side, you lose about 20 micron, for example. And say your wafer thickness is about 500 micron. Okay, 500 micron. Then that means you're going to lose already 520, 20 plus 500, the wafer itself, and then 20 on the right. So effectively, you are removing 540 micron from the ingot, but you are only using 500 micron of 540. Okay, so that means you ada curve loss about 20 micron on the left, on the right. Nanti dia akan repeating on the other wafer as well. So that is limited by the diameter of the wire saw. Okay, in this case, kalau you pakai diamond blade, for example, then it's limited by the blade width. Okay, blade width. So pemotong punya tu. So if that is very thick, then you're gonna cut through a very thick layer as well, and that thick layer will be represented as a curve loss. So maksudnya we have grown such a nice monocrystalline ingot of whatever specification that we wanted, but then eventually it's gonna be lost, right, from the production because it's lost through the curve loss. Okay, so during the slicing process, this is what manufacturers are trying to reduce, the curve loss. But you cannot eliminate the curve loss because you need to do the cutting anyway, right? So that's why kalau you follow dalam if you read solar industry, there's a new method called, you can read this through later on. It's not directly related to our course, but then it's very useful. It's called direct wafer technique, direct wafer growth technique. So how does it work? You search for yourself, right? So maksudnya if you use direct wafer for solar industry, not for IC. IC still pakai ingot macam biasa. So if you use this direct wafer technique, you eliminate the need of ingot growth, which is energy intensive, and then you also eliminate the curve loss during the slicing process. So maksudnya bila you grow guna direct wafer ni, direct wafer technique we call it, the wafer is ready as it is already, so you don't have to cut in between and suffer from the curve losses. Okay, so that's what manufacturers are trying to invent or innovate in order to come up with a totally different or new process in order to eliminate the curve loss altogether, and also eliminate the need for energy intensive Siemens process, brush recurrency process from the wafer fabrication or wafer growth. Okay, you can check that online, direct wafer. So as far as the current technique is concerned, for example, if you talk about the ingot growth for the IC fabrication, so there are still challenges remaining. For example, we want to reduce the curve loss as much as possible. So that means we nak reducekan habuk tu lah while cutting. So that essentially means reducing the diameter of the diamond, and then the ciliary abrasive on the wire saw as well. And if you talk about solar industry, so I can just mix up between solar industry and IC, because we have quite a number of solar manufacturers in Malaysia, so worth it for you to know. Solar industry is going for lower thickness. So currently we are using about 180 micron, some 160 micron. And the roadmap is showing that we're going to go into lower thickness in order to save material from the silicon. Okay, so bila kita save material, so essentially you are reducing the cost of the wafer, and that will bring down the USD per watt as we presented last time during trade 6, right? The benchmark, the technology cost benchmark for solar cell is USD per watt. So USD is how much do you spend in order to get the solar cell to be functional, over the watt, which is the wattage that you are extracting, the power that you are extracting from the solar cell once it is functional. So in order to minimize the dollar per watt, you have to minimize the dollar and increase the watt, right? And one way to do so is by minimizing the material consumption in the wafer. So that's why ITRPV, International Technology Roadmap for Photovoltaic, or ITRPV, is predicting that the wafer thickness is going to go lower. And if you want to cut thickness, a lower thickness of silicon wafer, it's going to be more challenging because as the wafers go thinner, it's going to be more and more brittle. Okay, like bila potong dia lagi senang pecah. Okay, sebab dia tak ada mechanical integrity, right? So it's very very thin, and you cut with the same amount of pressure, for example, through the ingot or through the bricks, it's going to be breakage everywhere, for example. And it's equally challenging to have process consistency if you want to cut through to maintain the curve loss, wafer thickness, damages on the wafers, and all the stuff. Okay, so these are among the things that you have to know while discussing about slicing or cutting of the wafers. You don't have to worry about this VPL because this VPL is one simulation platform that can be used in order to simulate the production of wafer or for silicon solar cell industry. So don't have to worry about that. So this one is another representation. If you look at the wafer preparation, the industry itself is not a clean process. It's not a clean process. So it's not a clean room type of thing. Dia tak pakai bilik bersih. So we're going to discuss after this topic. We're going to go through wafer characterization, and then we're going to jump into clean room, bilik bersih, sebelum kita start the very first process of the fabrication on the ready wafers. Okay, so if you look at this image, for example, the sewing process. So it tells already, right? It's not a clean process because by the look you can tell that it's not that clean. Okay, so this is what it means, or this is how it looks like on the wire sewing machine. Okay, so those are the wires like that. So semua ni wire. So macam tu. And then ni dia punya roller dekat ujung. Then you're gonna put your bricks or the ingot in between. Later on, they can turun and cut through the brick. So this is how it looks like. For example, you have silicon ingot here, and then it's going to run through the wires. Okay, run through the wires, and then with the slurry on the wires, so it's gonna cut. So they can fit kat sini, and then they can keluar sini. So that's how it looks like. You can watch on the YouTube later on. Go to this link and see how the cutting process looks like. Right? So the saw wire is going to pass through every single part of the wafer in order to cut through. So if you zoom in, okay, this is how it looks like. So this is the ingot, if you like. You just exaggerate the length, for example, to be the ingot. For example, if you're talking about the cylindrical ingot, then that's how it looks like. So the wire is in between. So this is the thickness that you want to cut. Say, I don't know, say 500 micron, for example. Katalah you wafer thickness. And then this is the region that you are cutting through. Okay, yang habuk tadi tu, cutting through using the wire sawing process. So that will be the curve loss in between. They can loss kat sini and loss sini. So if you repeat that across the ingot, so just imagine if you lose about, say, 20 micron per location here. So just imagine how many spots do you have across the ingot times 20 micron. So kalau you ada, say, 50 spots, so that's like 50 times 20 is 1000 micron loss across one ingot, okay, for example. So yeah, with thickness 270 to 100, depending on what do you want to do. And then the curve loss is quite a lot as well. So you can also convert that into kilogram of loss. Okay, so this is by Meyer-Burger slicing system. Okay, so one of the examples that we have in the manufacturing. So another one is diamond tip or plated sauce. So need to pakai diamond tip in your concept. So it's actually the same thing, but the other pro and cons if compared to another the diamond wire technique. So you have the cutter or the diamond tip plated sauce as the wire, if you like, here. So this is what the area that you cut or is going to be lost, and this is your wafer thickness that you're going to use eventually. So then you have your abrasive here, and dotted here are all abrasive. Okay, so abrasive to enhance the cutting process. Dia lebih kasar, and then you can cut more efficiently. All right, so let's go back to the whole flow. So the silicon crystal is sliced using diamond tip saw into thin wafers, sorted by thickness, and we have discussed a little bit about kerf loss. And then it's gonna be after the cut, the wafers below you cut. Do you expect the surface of the wafers to be smooth or rough when you slice the wafers using diamond wire saws or plated or diamond blade? Do you expect the surface of the wafers to be smooth or rough? Rough, okay? So rough kan, just like the effect of bila you sandpaper, right? You pakai sandpaper, you sandpaper the surface, even though it may look smooth by naked eyes. Kalau kita tengok dengan mata nampak mungkin smooth, but if you zoom into microscopic level or nanoscopic level, you'll see defects everywhere. Okay, you see they akan rough and damage here and there, non-uniform and damage. You have defects essentially, right? So that's why you need to have lapping process. Okay, lapping will follow the slicing process in order to remove all the roughness, all the defects supaya dia akan jadi very smooth. Dia akan jadi very smooth on the surface before we proceed with our next process. And then we follow that with etching process using chemical in order to remove all the defects using a chemical. So we're going to discuss later on what sort of chemicals that we use in order to remove all the defects, and then followed by polishing process before the wafers are ready from the fabrication. Okay, for the fabrication. So yeah, another graphical representation. So we cut the ingot. So remember, we remove the seed and tail. Say if this is the seed, say this is the seed, for example, then the other side should be the tail during the growth, after the growth. So kita potong dua region ni. So you're going to be left with almost perfect cylindrical silicon, and then we grind in order to remove certain flats. Okay, in order to mark whether it's P type or N type, 1001, according to what we learned last time. Okay, then this is another example. This is what you use in order to control the diameter, especially after the growth, because after the growth it's going to be very rough and zigzaggy on the surface. So masuk dari dipotong by diameter, by diameter to control the diameter. So this is another method to do. If you don't have the flats, then you have the notch, right? You have the notch we discussed last time. So this is the scribe ID. Yes, scribe ID. Usually you'll find this in wafer fab. Okay, scribe ID for every single wafer is different. It's unique. This is to avoid. This is to mark the wafer identity lah, macam IC wafer tu lah. So wafer mana kita guna, wafer mana yang ada problem. So that will be determined by the scrub ID. Okay, so then we know which wafer has which problem. So this is very unique for every single wafer. So that's a notch. So if you zoom into the edge of the wafer, then it's going to look something like this. It's going to have some bevel. So it's not like a square, you know, that kind of like that. Then your wafer is into the center. Ujungnya dia kayak ini. So this is the region. Right, so now I want you to search online try to Google what is the chemical that we use in order for us to do saw damage removal. Okay, you will search what is the wafer that we use, the chemical that we use in order to do saw damage removal. This step, we want to remove all the defects. So you search and then you share here. All right, KOH. What is KOH? Faris, can you write down the full name? Or has anybody found something else? Right, alkaline solution of potassium hydroxide. Okay. How about others? Do you find anything else? Any other solution that can be used? So one is KOH. So any other? Anyone? Akila, did you find anything? Akila? So wet chemicals for saw damage removal process. Okay, please write down. You can unmute yourself. Anyone? Tima, okay, Tima, hydrofluoric, HF, and nitric, sodium hydroxide. Most alkaline can be used. Yep, all right, the common one, yeah, the common one is you can use either KOH or NaOH. Alkaline, both are alkaline solution. So potassium hydroxide, well, you can also use Tima. Tima is also alkaline. But the most common one is KOH and NaOH. Okay, sodium hydroxide, potassium hydroxide. You can also use Tima with high concentration. There is a certain concentration that you have to use in order to remove the damage. Okay, if you use the concentration too low, then it's going to etch the surface to be pyramids. And nanti kita akan belajar in the etching process. So you normally probably have that kind of roughness after the slicing process, and you want to end up with a perfectly smooth surface. You want it to be smooth and damage-free surface. So mula-mula itu mungkin very rough, microscopically very rough. So you have to etch using certain concentration in order to remove all the defects. Okay. So these are among the examples. For example, if you wanna say you run 200 mm or 8-inch, this one is 12-inch. Okay, so these are the common one, 200 and 300, common one. Okay, so thickness, some using 700, some using a 500 micron. So this is the area, weight, and the rest. Okay, so examples of wafer dimension and attributes. For example, if you run 200 mm 8-inch versus 300 mm, and well, this is considered old school version of the die size, sebab dia tak banyak, so only 88 and 232. So if you use the same area of a chip, for example, on 200, say if you can fit 88 dies, and then if you run the very same chip dimension on 300, then that will fit up to 232. Okay, kalau dia punya chip ni the very same chip, but you just upgrade the size from 8-inch to 12-inch. So that's the difference in the number that you can get on the very same wafer. Tapi sekarang ni we typically have so much more of the chips on the wafer because the chips are getting smaller and smaller. So so you're gonna have like thousands of different dies, right? So another example of specifications, if you run say 300 mm or 12-inch, of diameter. So you need to control the diameter of the wafer to be plus minus 0.2 mm, plus minus 0.2 mm. So see the tolerance. So your diameter is 300 mm, and you can only afford to have variation of 0.2 plus minus. So you can only go up to 300.2 or 299.8 minimum. So the fluctuation from the supplier ataupun if you supply the wafers, so you can only afford fluctuation of 0.2 plus minus. Okay, and your center target is 300 mm. So say if you are using 775 micron thick wafer thickness, and then you can only afford a variation of 25 micron plus minus. Okay, so warping ni dia punya warp ni surface warp. I'm going to show you later on the real specification online. So you can only afford 100 up to 100 micron, and then thickness variation, total thickness variation, we call this TTV usually. I'm going to show you soon online. So you can only afford a variation of 10 micron across the wafer surface. Kalau you measure say 9 point, so maksudnya you ada say that wafer, and then you are measuring 9 point, maybe 1 point in the center, and then say 1, 2, 3, 4, 5, 6, 7, 8, 9. Say if you measure this 9 point, you can only, and then you get the thickness variation of the wafer, and then the difference, the variation between this 9 point can only be up to 10 micron maximum, ataupun within 10 micron. Tak boleh lebih. Kalau lebih, you won't be able to use the wafer for your production if you are on the customer side. So it depends whether you are the supplier of the wafer or the manufacturer of the wafer, or you are the customer of the wafer. Kalau you are the supplier, then you have to control within this level, this specification. If you are on the customer side, so that means you are perhaps under, well, normally we have it under QE department, quality engineering, or QA we call it sometimes, quality assurance, or sometimes we even call it QC, quality control, but essentially they are doing pretty much the same thing. And one example, one position, for example, that will be responsible for this is called, say, QE engineer or SQE, supplier quality engineer, to make sure that the incoming wafers are within specification that we can afford. Okay, maksudnya kalau you are the manufacturer and supply this kind of variation, so you have to confirm that every single time the wafers are coming in with the very same specification within the control. Okay, my thickness tadi lebih more than plus minus, and then the diameter plus minus, TTV plus minus. So all need to be within the spec limit or control limit of the wafers. Okay. So then you have some other parameters as well. You have to confirm and make sure that they are not out of control. So let me just show you. Just go out of this and share the specification of the wafers, so that you can appreciate what are the specs needed in the real manufacturing. Okay. Sorry, let me share with you. So first, okay, good. Okay, let me share the page. Share content. Right, can you see the page, the website on the screen? Please confirm. All right, good. So this is one example, wafer supplier page. So let's see what do they outline in terms of wafer specification. Let's just go down. You can come back to this later on. So see, okay, they are selling silicon wafers. And then this is the wafer, the ingot before it is cut into wafers, and these are the wafers in cassette. Typically 25 wafers per cassette. So let's see in the table below the summary of wafer specifications that are guaranteed by the manufacturers. Okay, so you can see here, just zoom in a little bit. Okay, so cubic silicon in terms of crystal structure, melting point 1400 as discussed during Czochralski technique, so silicon density, and then they provide either from FZAC process, right? The wafers can either be from FZAC process, can also be from CZAC process, can also be from MCZAC process as discussed last time. So the wafers can be undoped intrinsic, or it can be boron doped p-type, it can be phosphorus or arsenic doped for n-type. Okay. So resistivity varies. So if you don't do any doping, for example, then obviously the resistivity will be very high, over 1000 ohm cm or 10,000 ohm cm, because you don't have any doping. Therefore, the electrical conductivity will be very poor, hence high resistivity. If you, on the other hand, if you have p-type, and then, well, it ranges from different across different resistivities. It can be from very low resistivity, like 1 times 10 to the minus 3, or 5 up to 5 times 10 to the minus 3 ohm cm, and it can also be up to 20 to 100 ohm cm. So if you see this, for example, let's just recap a few things. If you see this p-type from 0.001 down to 20 ohm cm kat bawah sekali, so which wafers are lightly doped? Which category is lightly doped? You can unmute yourself or write down in the chat box.
20.
20 apa? 20 ohm cm, lightly doped. Why? Why is it so?
Because it is the highest it has the highest resistivity compared to the others. Yeah.
Right. And remember, conductivity is the inverse of resistivity. Okay, conductivity is the inverse of resistivity. Yeah, conductivity equals to 1 over rho, right? So you can see obviously here, if your resistivity is the highest, then your conductivity will be very low. So that means it's lightly doped. So it has p-type, it has boron dope, but then the level will be very low. So kalau you nak tahu the exact level, so you have to go back to the curve that we learned in 386. Remember the doping level again, the resistivity against doping level curve. So you can check the line there. If you go for certain doping level, then you're going to end up with 20 ohm cm. Okay, so the same goes to n-type as well. So ranges of resistivities are provided by the manufacturer. Then oxygen content below 8 times 10 to the 17, carbon content below 5 times 10 to the 16. Okay, so this is more towards the packaging. How do you package? Well, typically it's vacuum package. Maksudnya when your wafers are put into the cassette and then closed, and then it's going to be put into a plastic and then vacuum sucked. Vacuum package, dia akan sedut, and then dia akan jadi very compact sebab dia vacuum suck. Right, so let's see what other specifications outlined down here. Orientation I mentioned. Orientations I mentioned 1 0 1 1 1 1 1 1 0. Okay, standard size, thickness, polishing. Okay, ini untuk kita order lah. So if you're one of the users, for example, and if you want to buy these wafers, then these are among the specs that you want to have a look at. Right, so let's see what else we have on the other one. Right, you can see the next page, right? Siltronic, can you? About the Siltronic page. Okay, can see. Right, good. This is another supplier essentially. So they supply silicon wafers. SOI is silicon oxide on insulator. SOI, we call it SOI. So you can also see some specifications outlined. So 1 inch ada, 2 inch ada, 3 inch ada, 4 inch, 5 inch, 6 inch. So for this particular application, that means Siltronic has ingot growing process for 1 inch, but the others ingot yang very small, 1 inch is like 2.5 cm diameter. Macam wafer yang kita ada dekat dekat no lab kita pakai 2 inch. 2 inch is the second one, 5 cm. So 1 inch is even smaller than that. 2.5 cm punya diameter je. So that means the ingot process and the crucible will be very, very small. Okay. So 3 inch dia ada ingot growth, 4 inch, 5 inch, 6 inch. Okay. So typically more towards lab application, I believe, because they don't have anything above 6 inch. So N-type, phosphorus, antimony, arsenic as the dopants, and then P-type is usually boron. Okay. So Characterisation or float zone. So it depends on the either growth process do you want. Orientation, different are provided. Okay, tolerance of the orientation. Okay, thickness. You can see standard thickness. Say, for example, if you want to use 6 inch, so that means they are offering 675 micron wafer plus minus 20 micron. Okay. So ada juga on request if you want to have 120 micron up to 15 cm pun ada. So that means very, very thin. Very, very thick, sorry. 1.5 cm ataupun 15 mm. So that's relatively thick for a silicon wafer. So particle count. So for example, if you are choosing 6 inch, then particle count is less than 15 on the surface of the wafer. And TTV, whatever that we discussed just now, right? Total thickness variation, less than 10 micron on this thickness. So, well, they have TTV for SSP, single side polishing. So that means if you have the wafers, only single side is polished and the other side is not polished. So maksudnya, one surface is shiny and the other surface is not shiny. So if you have double side polishing, DSP, so you have both surfaces polished. So you can nampak dua-dua shiny, So bowing less than 40 micron means bowing ni means wafer tu dia bow how much? Dia bengkok, dia bengkok. So you don't get to see that the naked eyes, but then if you do some measurement, it can tell you how much bow do you have, right? So surface roughness for a polished surface is controlled below 1 nanometer. So that means a very, very smooth surface. So yeah, this is among the example that you have on the wafer spec. And then let's have a look at another one. This is from microchemicals. So ingot, and then these are the flats that we learned in our previous class. The cutting process. Okay, the diamond, the wires with diamond slivers. So ini pakai diamond, diamond abrasive for the cutting process. So that's how the wires look like while cutting the ingot. And then the next processes. Kita belum cover lapping and yeah. So let's see this. So thickness variation, total thickness variation, TTV, bowing, right? You can I'll upload this PDF later on the e-learn. You can see what is bowing, how is it measured and stuff like that. Warping, micro roughness, less than 1 nanometers now. So you can see the micro roughness. Even though you've done the lapping process, it will still show you some micro roughness with a tolerable level, right? Okay, so that's pretty much what you have to see. For example, if you are the quality control engineer or supplier quality control engineering, some of the make sure in your incoming wafers, okay? Kita panggil incoming wafers sebab wafer tu bukan, it's not manufactured by ourselves. It's provided by the supplier. Incoming wafers. So specs of incoming wafers. Specification of incoming wafers. So you have to make sure that all the critical parameters are within control. Okay. So usually, how do you know what are the specifications? Soalnya dalam fab dia akan ada satu department yang control all the specs. Okay. Kalau macam in Silterra, we call it DocCon team ataupun document control team. So they will handle and they will update all the specs related to the incoming materials, spec related to gases, specs related to processes, specs related to preventive maintenance of equipment, specs related to our chips, specs related to pretty much everything that we have in the fab. Okay, from the incoming punya material sampailah dia keluar daripada wafer fab. Okay, from A to Z of the cycle lah, if you like, of the process cycle, everything has a spec. So maksudnya bila you are a process engineer, so you will refer to process specification almost every day. So if you see any variation in your process later on, we're gonna see. So you always have to go back to the spec and check what is the specification of this particular process. For example, if you're doing deposition of oxide, silicon dioxide by say CVD process, then there are control specification for that particular process. So you always have to open up the PDF of that spec almost every day to make sure that your process fluctuation or variation or uniformity is always within the spec. And the same goes to the gases and the wafers and the slurry. Even the slurry has a spec, okay? Perlu ada certain size, certain variation. Then if you're doing wafer sewing, your wire, your roller and everything, okay? And then it even spells out for an equipment engineer, for example, if you're an equipment engineer and you have to do maintenance, there's also a spec for you to follow. For example, if you have to do weekly preventive maintenance, weekly maintenance is essentially what we call that PM. If you're a process engineer, PM, preventive maintenance. So there's a spec for weekly PM, there's a spec for monthly PM, there's a spec for quarterly PM, semi-annual PM, annual PM, biannual PM. So a range of different PMs for equipment engineers to handle. Okay, so those are one of the things that you have to be familiar with, especially later on kalau you not join quality departments, and these are the amount of things that you have to know at least, right? Okay, let's talk for a while for the first session. Do you have any question? We're going to continue with the lapping and see how many can we get through. In the second session, we might go into characterization a little bit as well in the second session. So do you have any question for now? Okay, anyone has a question? No? All good so far? Still easy, right? Easy to understand, isn't it, at this point? No confusion, very straightforward. Okay, all good? All right then, so kalau tak ada soalan, let's just have a 5 minutes break. Sekarang 10:51. Let's come back at 10:56, more or less, to continue with our second session, right? So I'll just turn off my camera first, and I will come back in 5. See you in 5 minutes. Right, shall I continue? Okay, let me share with you the sewing process. Just a short video. Okay, can you see the YouTube page? Apa? Can you see the page? Okay, all right. So let's just go through briefly this few minutes video. I won't go through the whole 5 minutes. So that's the machine. Just go for it. You cannot hear the audio, right? Can you? Can you hear the audio? Audio of the video. Can you see? Can you hear it? Boleh nggak, Kak? The audio? Can I cannot? Ah, okay, all right. But that's all right. Let's just go through the graphics then. So that's how it cuts. Okay. I just go through briefly. So yep, that's how it cuts. So in this case, 100 micron. It's in Japanese, by the way. So so that's the roller, the wires. That's the diamond abrasive. Okay. So that's the liquid. Right. So that's pretty much how it looks like in the wire sewing process. It can even be simulated as well. So that's how it looks like. So the wires, so the slurry comes in. Okay, so yeah, just a brief one. Let's go back to the slides. So this is still outside the fab, yeah, okay? Still outside the fab. Tak masuk fab lagi ya. Ini baru dekat silicon manufacturer aja. We haven't started anything. We haven't started any fabrication processes yet. So this only on the wafer preparation side. Okay, so all right, so can you see the slides now, just to confirm? All right, thank you. So the next is the lapping process. Okay, lapping process is here to remove all the damages from the slicing process or from the cutting process. Okay, so the slice wafers are mechanically lapped using counter rotating machine and aluminum oxide slurry. So again, we are using slurry untuk lap. So you have your top surface here is rotating counterclockwise, and then the bottom one is rotating clockwise direction, in clockwise direction. So they are moving into the opposite direction with each other. So this will flatten the wafer surfaces, make the wafers parallel, and reduces mechanical defects like saw marking, especially saw marking. Okay, so you probably have some micro scale roughness after the slicing process from the sewing process. So this will smoothen the surface by the lapping process. So the correct wafer thickness is also produced via lapping. So you can also get to the thickness that you intend to have in order to produce by using lapping process. So you're gonna have like batches of wafers. So for example, you ada satu tray ni. So you have like 4 in this case. So you may have a lot more depending on the machines that the manufacturer uses. So in this case, you have like 4 per tray, and then you have like a couple of trays. In this case, 4 together in one batch in one machine at the same time, right? So ideally you want to run as many as possible wafers in the batch, because that will increase the throughput of the process. Okay, throughput, we normally say this is another word that you have to be familiar with if you want to go into industry. Throughput, or the capacity of wafers, number of wafers that you can run within an hour, for example, right? So higher throughput means you can run more wafers in the same process per hour. Okay, so throughput. So every single process in the fab akan ada throughput. So in this case, walaupun dia tak masuk fab lagi, it's still outside of the fab. So manufacturer yang prepare all the wafers pun ada their own throughput juga. So this is another word that you have to be familiar with. So another form of another representation of lapping machine. So this case is by Mitsubishi Materials. So after the lapping, wafers are etched in solution of nitric acid, acetic acid, or sodium hydroxide. So the common one is sodium hydroxide, or KOH, to remove microscopic cracks and surface damage produced by the lapping process. So even though, if you see here, even though the lapping is intended to remove the damages produced by the sewing process, so the lapping process itself produces some cracks and defects as well. So it reduces, but then it has its own called inherent limitation. In this case, the defect on the surface. So then that's why the etching is required right after the lapping process. Okay, so if you look at the sewing and then the lapping, so both processes are mechanical in nature. So dia lebih kepada pergerakan, so it involves pads and slurry and movement, right? So it's very mechanical in nature. But then if you talk about this process, the etching is very it's more chemical thing. It's more wet chemical nature. Okay. So then we follow the process with polishing. After the etching, wafers are polished in a process called CMP, or chemical mechanical polishing. So we have this CMP department in Sultana as one department. So normally, departments are divided into roles. Okay, in the case of Sultana, for example, if you talk about the general department, kalau untuk fab punya case, fab punya case, dia akan divide the main departments into fab operation and fab support. Okay, fab operation and fab support dalam wafer fab, to CMP and others. Fab operation is the departments that do all the main processes in the fabrication process, fabrication cycle. So you have like lithography, oxidation, etching, implant, all the stuff. And then you have another group of department called fab support. So this is where all the QA ataupun QE or technology development, what else? Reliability, failure analysis are located. Fab support. So fab support ni dia supporting role. It plays the supporting role to the whole fab operation. But fab operation is the daily process that you have to do. Daripada wafer to start the very first step until the very last step. So it's all the fab operation. So dalam every single group you have your own equipment engineers, process engineers, application engineers, and then in the fab support you have FA engineers, technology development engineers, fab integration in the fab operation, QA engineers, all the stuff, right? So for CMP process, it's in the fab operation side, right? Because CMP is one of the main processes involved in the fabrication process. So wafers are held in a hard ceramic chuck and polishing using a slurry of silica powder. So again, you can see here slurry, but in this case silica powder, DI water, and also sodium hydroxide. So they can, so the process is something like dia akan pakai polishing pad, polishing pad ni macam if you can imagine you pakai, well, if you do the dishes, right? If you do the dishes, you wash the dishes, kita akan pakai sponge kan, sponge yang you nak rub on the plates punya surface kan, pinggan and so that's kind of thing. So the polishing pad will be something like that. It's just that it's automated, so dia akan ada dia rotation, speed, and all so on and so forth. So just like what you can see here, right? Polishing pad. They can polish on the wafer. So this is the wafer across the wafer. So the wafer semua ni, wafer. So these are the pads and right. CMP process. We're gonna go through in detail later on. All right, so that's how the pad looks like. So you have the upper polishing pad, lower polishing pad. So the wafer is in the middle, and then you have your slurry deployed in order to do the CMP process. Okay, so you ada macam pad atas bawah, and your plate or your wafer is in the middle, right? So wafers can be polished in single side or double sides. So both sides CMP leads to more expensive wafers. So kalau you polish both sides, so you're going to get more expensive wafers. So if you are the manufacturer, CMP, the silicon wafer, then your double-sided polishing will be more expensive than single-sided polishing punya products. Okay, so again, the wafer specifications. So we have seen some of these properties or specs previously. So we control wafer diameter, flatness, micro roughness, oxygen content, micro defects, particle area, epi thickness, if there is epi at all on the layer or on the wafer. So epi is a very thin layer of a specific material, especially if you're the manufacturer selling epi wafers. Kalau you jual wafer, yeah, then is it the wafers lah, tak ada epi layer. So kalau in this case it's epi wafers, so that means a very thin layer grown on the silicon with a specific thickness, and that layer thickness and the specs are also controlled in this case. So another process in the wafer preparation involves gathering process. Okay, so gathering, bukan gathering dia punya maksudnya lebih kurang macam gathering, but then it's gathering. So it's a process of removing harmful impurities or defects from active regions of the silicon wafer. So remember when you have a MOSFET, for example, okay, if you have a MOSFET and this is your silicon wafer, so before you have the device on, or in fact after you have the device on, gate oxide, source, drain, okay. So where is the active region of the wafer? So try to take a cross section. Try to relate to the first sentence. Process of removing harmful impurities or defects from the active region of the silicon wafer, where devices operating. So in this case, if you look at the cross section of my sketch, where's the active region of the device? Can you point? You can just say, I'm in the south. I'm an active region of the device in this case. If you look at this simple MOSFET. Anyone? Any ideas? Any guesses? Alia? Any guess, Alia? Where's the active region of the device or of the operation? Any guesses? Okay, Alia said center. All right, okay. How about Go? What do you think, Go? Where's the active region of the device? What do you think? Any idea? Don't know, right? Okay. Fatin. Fatin Nur Tahira, what do you think? Any guess? It's okay, just guess. That's fine. Well, let's have 2 more guesses. Shafika, anything? Shafika? Kat mana active area ni? Dalam device ni. Center, okay, is it center, right? Okay, last one. Any other? Juaria, what do you think? So we have few centers. Center as well, right? Okay, you say center. Okay, essentially, the active regions, well, yes, you have the channel in the center. Oh, sorry. Channel in the center connecting your source and drain under the gate oxide. But if you look at this cross section, the active area are the upper half, if like, not even half lah, tak cukup half pun sebab kita pakai the very top region dia untuk buat device. Okay, so that means the bottom half or more than half is not an active region. Okay, and kat bawah ni is a passive region lah. Lawan active is passive, right? So region that doesn't accommodate the device effectively, right? Okay, so in this case, we want to do gathering to remove harmful impurities or defects from the active region. And the active region in this case is like in the top part of the silicon where you fabricate your source drain and then your gate ox and then your gate. Then those are pretty much the active area. So how do we do that? By providing an alternative location, a getter, we call it a getter, ataupun satu tempat untuk kita kumpul all the defects at one place. Macam you have to like suck all the defects at one location and then eventually remove the defects from the equation altogether or from the physical wafer altogether, right? So we call that as a getter. Okay, so that's why proses kita panggil gathering. So wafer on high temperature treatment, typically around 1050 nitrogen ambient, in order to perform the gathering process, right? So oxygen evaporate from the surface, low oxygen content near the surface, and then this will create a denuded zone or defect-free zone suitable for device fabrication. So I'm going to share with you some details on gathering process later on it. Okay. So additional thermal cycle can also promote formation of oxygen precipitate in the wafer, can be used for impurities gathering. So oxygen precipitate also helps to improve the gathering process. Okay, that can be done as well. So this is a cross section of a defect-free near surface region of a silicon wafer. So that means that is the top surface. So this is the bottom area. So the top is defect-free. Okay, lower part shows silicon dioxide precipitates used for impurity gathering. So we use silicon dioxide in order to gather. So silicon dioxide is just a platform or medium for you to gather the impurities, and then eventually the silicon dioxide will be removed altogether from the silicon, even though it's already in the passive region. Okay, we still remove it anyway. So in IC manufacturing, primary unwanted impurities are metals which increase recombination. So we discussed that in 386. We discussed about the shadow traps. We discussed about the deep level defects. Remember last time? So if you can recall this, we have EC, conduction band, energy level, EV, and then you have EG, the mid gap, right? oh sorry, this is the mid gap, not EG. EG is here, the band gap, and then this is the dashed line is the mid gap. And then if you have metals like copper or iron, for example, then they will end up as deep level defects close to the center or close to the mid gap, right? Which is deleterious or very, very bad for device operation. And on the other hand, we also have shallow traps, okay? Like some other metals, tengok dia punya energy level dia kat mana. So shallow traps causing the recombination, okay? So they are bad because they cause recombination. And then the metals, or the unwanted impurities, are metals which also segregate to interfaces, resulting in interface states. So these are all interface states, right? So they'll suck the carriers and trap the carriers, and end up you don't have the carriers or lesser carriers in the devices. Precipitation and also provide conductive path. Okay. Later on, we're going to see you want certain region of your wafer, kata you buat MOSFET. So you want certain region to be conductive, and you want some other region to be insulators in nature, right? So kalau you ada metal somewhere there, for example, in the insulator part, dia akan provide alternative conducting path. Sebab metal is conductive, and you don't want that area to be conductive. But due to metal, that area becomes conductive accidentally, right? Accidentally, kita tak boleh control. So that's why you have to really control the precipitation by performing the gathering process. So desirable to remove metals to outside active area region, backside, or in the bulk. So these are the typical passive areas. So sources of unwanted impurities. So the impurities that we have, say metals or whatnot, may be coming from the melt, right? Remember, from the melt, from the ZAT process. So that will incorporate some unwanted impurities as well, if it's not clean, right? If it's not well maintained. So it may come from chemicals from a previous treatment, right? Cleaning or etching or resist. Later on, we're going to discuss about resist. Or handling process by the wafer tracks, tweezers, boxes, particles, scratches, for example. Okay. Process chambers in the stainless steel, in the quartz, in the crucible, in the chambers that you send the wafers to go through. So they may be sources of the impurities as well. Okay, the polished surface versus the rear side. So the gathering, so this is another way to do it. So the argon amorphizes the backside of the silicon. The wafer is heated to 550, glue the silicon. However, the argon cannot be absorbed by the silicon crystal. So it precipitates into microbubble and prevent some damages from annealing, right? This is another way to do it. All mobile contaminants are attracted and then captured. All mobile metals are attracted and then captured by the argon stabilized damage. So induces damage in order to trap all the mobile ions, mobile contaminants, and then once they're captured, they never leave the site. So you can figure out on how do you remove the area then, okay? So we're done with vapor preparation. Is it okay so far? We're gonna move on to wafer characterization. So far so good? 11:20. So far so good, yeah? Okay guys, semua? Are you up and running? Is it okay so far? So was it good, right? Okay, so let's move on to wafer characterization. So we have learned about the wafer preparation technique and all the steps involved briefly. And then we're going to go through important characterizations that need to be done to the wafers, okay? So remember, you have to prepare the wafers, characterize the wafers, understand the properties of the wafers, then only the wafers will be ready for the first fabrication process, okay? So we are almost into the fab already. So now let's move on to characterization. So we have discussed about the steps involved in wafer preparation, the flow chart. Okay, so we discussed about curve loss. We've discussed about wire sewing, diamond blade sewing, and then we've discussed briefly on how can we minimize the curve loss. Right, we've gone through the role of CMP process during the wafer preparation, and then just gone through the gathering process and why is it important. So I'm just gonna skip this because we just went through the details. Right, so when we characterize the wafers, we have to look into certain parameters, and we've discussed some of those during our first classes now. So we've gone through the specifications on commercial silicon. So you've seen we control the thickness, the total thickness variation, the flatness, the bowing, the warping, the particle size, and whatnot, right? So these are among the quality measures that we have to do in order to be sure of the properties of the wafers. So physical dimension, flatness, micro roughness, oxygen content, crystal defects, particles, bulk resistivity, and these are only among the parameters that you have to control, not everything yet, right? So there are many more parameters depending on the wafers are going to be used for which particular applications. So if your applications are more sensitive to the qualities of the incoming wafers, then definitely you have to control over more parameters in the incoming wafers. On the other hand, if your final devices are not that sensitive to the incoming wafers, then the parameters for you to control will not be as many as the first case, right? So it really depends on the applications of the devices and the sensitivity of the devices. Right, the first one you have to do is a very simple method that we call visual inspection. Okay, so dalam fab we normally call this VI, visual inspection technique. So this is also carried out in wafer manufacturer designer. VI. So has anyone done any inspection under the microscope for your FYP last time? Anyone did any sort of inspection on microscope? Ada? Tak ada, semua pakai yang lagi canggih. Microscope is too simple, isn't it? So microscope is one of the most simplest characterization that you can use. Simple one, just macam microscope, you just tengok apa abnormality on the surface and stuff like that, right? A very simple one. So you can see, for example, pernah pakai, right? What do you check, Juara? You tengok apa under microscope? Right, crystal. So during your FYP? During FYP, yeah? Okay, right. Okay. So it's a very simple characterization technique. And in fact, I think the most simplest one, I would say. Simple je, but then you can catch something. Okay, you can catch something. So if you talk about manufacturing, we are using, we call it as inline characterization. Inline characterization. Ni macam lebih pada inline characterization. It means you have all the characterizations that you can use inline, maksudnya during mass production, in order to inspect the quality of your products. Okay, so an optical microscope is one of the inline characterization equipments or techniques involved, right? For example, if you want to print, for example, if you want to print this chip, kata you nak print this, bukan chip, this feature, this square feature of this size, say, okay, you look at the scale bar there, that's about 200 micron. So this guy has to be, I'd say probably 150 or 170 micron times 170 micron. Okay, so say that is the feature that you want to print by lithography later on. Okay, Then you check after the lithography process, after the printing process, you verify on VI, on visual inspection using microscope, and then you get to see this. Then you see this feature, and then you see this feature, see this, but you want to print this actually, and you get to see this, and rest. So do you call this as a good process, or is it a bad process? What do you think? You intend to print this, but you end up with all of the squares. So do you categorize this as a good process or a bad process? Anyone? Any idea? Come on, you can unmute yourself. Go ahead. Good process or bad process? Okay, Hazik, bad. Faris, bad. Any other? Hazik and Faris, why are you saying it's bad? Juaria, bad. Why are you saying it's bad? Kenapa bad? You can unmute yourself. Okay, Hazik, you got solid reason, right? So what is it? Kenapa bad? Very simple, right? A very simple reason, isn't it? So why? What is going on? What is the reason there? Hazik or Faris or Juaria? Kenapa bad? Faris, anything? This is a decision step. Okay, Hazik, can you repeat the question? Yes, well, you want to print the feature in the circle. You nak print macam ni. And then bila you print, bila you run the process, we're going to learn about the printing process called lithography, photolithography, printing using light. So after the printing, you got all these features dalam gambar ni. So then you go for visual inspection under the microscope. So after that, you have to decide, katalah you process engineer, you have to decide whether this is a good process or a bad process. And you said it's bad process. So why is it bad? Hazik? Don't know? Faris? Joria? Why is it bad? Different colors, okay, Joria, different colors, right? So you can see you want to print this, but you end up something like that, maybe. That as well, that as well, that as well. Like, yeah, any other reason? Do they have the same size exactly? From one square to another? One feature to another feature? No, right? So you want to print the second square there repeatedly, exactly of the same size, exactly of the same colors, exactly of the same everything, right? So but it ended up in range of features from smaller one to bigger one, lighter one to darker ones, right? So that is a very simple technique using an optical microscope for you to decide that it's a bad process or bad printing process due to whatever reason along the way, okay, along the way. But then you can tell already that it is a bad process. So when you do characterization, my point is this: when you do characterization, it doesn't have to be like always SEM all the time, always AFM all the time, or always TEM all the time yang lebih high end, lebih state of the art. But simple characterization technique like optical microscope, yang very simple, just put the wafers under the scope and then you just teropong tengok je kan. And then you scan, you move the stage to check across the wafers. That can already tell something, especially if the defects are visible by naked eyes. Okay. Ataupun you change the magnification a little bit because there are lenses kat sini. Ada lens, then you can change magnification macam you play with your camera, right? So you can change the focus and stuff like that to be able to visually inspect the features that are already printed. So maksudnya tak semestinya you go for high-end characterization technique to catch if there is any problem in your line at all, right? So in this case, a simple visual inspection will do. And in fact, if you do any process, we're going to learn later on, lepas you buat any process, usually, most of the times, it will be followed by a simple VI technique in the fab. Dalam process flow fab, say you have like 200 different steps, and there will always be VI after lithography, VI after etching, VI after diffusion, VI after implant, VI after thin film deposition that we're going to learn later on. But there'll be VI everywhere at every single station, right? After every single process, for you to be sure that you are doing the right thing, at least by naked eyes. Okay, so you can tell already that this is a bad process. So then after this process, after this characterization, you can already tell that something is bad coming out from the equipment, from the process. You can then stop the process immediately, stop the equipment immediately due to this defect, so due to this issue. Kalau you biar macam ni je, feature ni print sampai ke hujung fabrication process dan sampai ready chip, then you're dead. You'll be a dead meat. Kena potong lagi ya. Literally ya, literally bukan betul lah. So literally, so you have to catch the issue there, right there and then. So this is among the JDs or job descriptions of a process engineer, equipment engineer. So you have to make sure that this is caught. And the persons who are working on the scope will be the operators. Okay, operator yang akan tengok every single wafer. So let's say you have like 25 wafers per pot. Satu pot yang besar tu ada 25 wafers. So maybe you will inspect, I don't know, maybe 2 or 3. Dia takkan, you'll not afford to inspect every single wafer from the cassette because it's just too time consuming, isn't it? So you want to send the wafers through the process as fast as possible. So you can only afford to do sampling. So this is another thing that you have to learn later on, that fab will not characterize every single wafer. Instead, it will just sample the wafers in the cassette. For example, out of 25, depending on the characterization, normally only 2 or 3, some cases 5, depending on the sensitivity and the how crucial is the characterization. Well, typically, if you talk about the VI optical inspection, it's just like 2 or 3. So if you're talking about 2 per cassette, so that means you are picking wafer paling bawah, wafer paling atas, so that means wafer number 1, wafer number 25, and then wafer in the middle, maybe 12 or 13, right? Okay, so 1, 13, 25, or 1 and 25. And this sampling will pretty much conclude whether your whole cassette is okay or not okay. So if you sample only 3, do you think you will miss any defects in the middle? Do we have any probability of missing defects in the middle? If you sample 3 out of 25, what do you think? This simple decision making punya reasoning, this is not a high-end physics or whatever. This simple decision making punya reasoning. If you have 25 wafers per cassette, satu pot to 25, you can see this on the YouTube that I shared about GF or Intel. You can see the pots moving on the automated line tu, yang bawah tu. Then out of the 25, you only sample 3 je. And then do you think you will miss any defects along the way? What do you think? Is there any probability of you missing the defects in wafer 2 up to 12, 14 out of 14 to 24? Is there any probability of you missing the defects? What do you think? Simple reasoning. Before we move on. Okay, Haziq say yes. Right, others? Yes, we will. Right, Joanna, yes, we will. Any other? Any, let's say, 2 or 3 different opinions? Anyone else? Will we have a chance of missing defects in the middle? Kita inspect wafer 1, wafer 13, wafer 25, nampak semua okay So then you see this all over the array, maknanya all printed as this. But do you think we'll have a probability of having this issue yang tak sama color, tak sama size in other wafers that we did not inspect? How about others? What do you think? We have 2 yeses. Any no's at all? Izati, what do you think? Izati? Do I have a probability to miss at all? Ali, what do you think? Come on, simple reasoning here. There's no fancy physics here. Simple reasoning. Izati, go, Hadi, what do you think? I need to hear 2 more answers. You have 2 yeses. Let's hear 2 more. Come on. Yes or no? Do you have any probability of missing defects in between? In the wafers that we don't characterize, in the wafer that we don't inspect under the microscope. Come on, others, go. Yes, all right. One more. Is that the yes? Right. So the answer is yes. Okay. So bila you inspect only 3 out of 25, of course there'll be probability higher or lower. We're not sure, depending on the process stability, process uniformity, and luck somehow. Okay. So if you do some calculation there, 3 out of 25. So, yep, 12% will not miss. So that means, well, what does it mean? We have 88% of missing, right? So if you say 12% of not missing, so we have 88% of missing, isn't it? Of probability lah maksudnya. So we'll still have a chance of missing or skipping the defects lah. Just in case, kalau defects to appear on wafer number 4 or wafer number 6 only, but none on the rest, 7 only, or perhaps 23 only. So we have these cases all the time in the fab, right? All the time. So kadang-kadang you cannot explain by any possibilities of why do we have defects on wafer 24 but not on the rest? Sedangkan wafers tu dia go through the same sequence and the same chambers and the same flow and blah blah blah, same parameters, but why only on 24 but not on the rest? And for your information, we have this problem all the time. Okay, all the time, right? It's not a surprise at all. Okay, it's not like very strategic if you have all the wafers going through the very same process, same equipment, same everything will be the same. No, the answer is no. So that's why we have you as the potential process engineers or equipment engineers to troubleshoot where is the root cause, where is the probability, and how does it end up there. Okay, so that's part of the JDs that a typical PE process engineer or EE, we call it EE or PE. Normally dalam fab, kalau orang fab dia faham lah PE ni apa, EE apa. EE for equipment engineer, PE for process engineer. So this typically among the JDs of PEs and EEs, okay, or PEs, depending on the scope of the issues, right? So yeah, well, so that is a very simple reasoning that we learn, at least from this optical microscope. To me, one of the simplest characterization technique involved. So we haven't discussed yet about AFM, SEM, and light scattering, defect inspection, and all those stuff which are more fancier and can tell you more data, can tell you more results. Ini yang paling simple lah. And sometimes, for example, if you see if some defects are very visible, kalau defect tu very big, kalau contoh you dispense certain chemical on the wafers, you're gonna learn later on, and then the volume is not enough. For example, kalau you do wafer 8-inch and then you dispense satu chemical and then you spin at high RPM, but your spinning volume is not enough. Kalau dia enough, then you spin, it's gonna cover uniformly across the wafer, right? But if the volume is not enough, then you spin, they are kind of subjected to the force, right? The force outwards, right? So the distribution will not be uniform and the volume is not enough, and you're going to end up with something like a streak. So let me just show you an example before I finish. Kata you had a wafer, and then you spin the volume of the material in the center before you spin coat, so that you can distribute the chemical uniformly across the wafer, so that it ends up very uniform across the wafer. Tapi kalau your volume is not enough, for example, you're going to end up with something like this, a streak going outwards. Sebab kita punya spin kan, dia punya nature of the force is going outwards, right? They can distribute outwards. So dia akan keluar tapi it will not be enough to cover the whole surface because the volume is not enough. So therefore you're going to end up with something like this, the chemical streak. This is very operational because I'm trying to describe here from my own experience. I saw this quite a lot last time in the lithography process. Streak, S-T-R-E-K, streak sometimes, right? So this is one symptom of volume is not enough when you distribute. And this is very visible because it's very big. So it's not microscopic, it's not nanoscopic, it's very centimeter good lah. Centimeter for wafer pun dah 200 mm, 20 cm. So centimeter in size is very visible. So then in this case, you don't have to go through high-end equipment in order to catch this defect because a simple microscope inspection or VI will do. You masuk je Zam, you nampak. Ataupun kadang-kadang you tak nampak, you tak hantar wafer bawah apa ni, microscope pun you can already see, the wafer is full of the streaks. Tak masuk dalam VI pun, tak masuk dalam optical microscope pun. So these are among the things that you're going to learn in characterization, and you're going to experience if you do wafer fabrication punya career ataupun internship later on. Okay, these are among the things especially. Okay, let me just stop here. So we'll continue next Monday with AFM onwards. And then if we have time, we're going to move on into clean room. Okay, bilik bersih, before we start our first fabrication process, which is thermal oxidation. Okay. So any questions so far? Okay. No questions on characterization at this point? All good? Tak ada? So saya assume semua faham, tak ada soalan Right? Okay then, if there's no question, I'll see you next week, inshallah. Right? Okay, bye-bye, take care, assalamualaikum. And have a nice weekend as well.